Hey everybody, and welcome back, or if it's your first time here, welcome to this channel. I'm David Townsend. This is the Net Academy, where we are learning networks together. And now I am starting the video, the content on the mammoth protocol that is BGP, or Border Gateway Protocol. I cannot emphasize that enough. This is a absolutely huge protocol that destroys careers and actually makes careers. It is that big, and it's actually what makes the actual internet itself work. And there's a huge amount of features and configurations that you could do with BGP. However, just with like anything, we always have to start off with the basics before we start understanding and learning the more advanced topics like route reflectors, configurations and clusters and route targets and so much more. So in this video, what I'm going to go through is the basics. What is BGP? Why is it here? How is it different to interior gateway protocols like OSPF, like ISIS and others? And what are those BGP messages? What functions do they serve? And how does that help actually to progress to those and through those different BGP states? So let's get going onto the lab and let's crack on with the theory and of course the configuration itself. So there's two different ways to actually use BGP. There's eBGP, which stands for Exterior Border Gateway Protocol, and then we've got iBGP, which stands for Interior Border Gateway Protocol. Now the difference being is that when you look at this lab, what we've got is we've got some ISPs here, we've got an Enterprise B here, Enterprise A here, another ISP and another ISP here. Now eBGP is exterior, i.e. it's exterior from one network over to a network, from one service provider over to another service provider, from that service provider over to an enterprise, from the service provider over to a data center, whatever it might be. eBGP is quite literally connecting different autonomous systems together. And with eBGP, those links, those adjacencies are actually built on the interface's IP address, whereas iBGP is actually inside the autonomous system itself. So iBGP would be working maybe within the ISP1 here, and then within Enterprise B would have a separate instance of iBGP working in Enterprise B. The same for Enterprise A, and depending on the size, ISP2 here, but as you can see ISP3 isn't really big, so it's just one router to keep things a little bit simple. But iBGP is inside, it's interior to that autonomous system itself. Now unlike eBGP, with iBGP, the peering between different routers or different multi-layer switches, anything that's running BGP inside that same autonomous system, it's built using the device's loopback address. And by the way, I don't know why my pen is changing the colors. I'm going to have to look into this. I've not done anything with it. It's just randomly changing the color. Makes it look more colorful, I know, but anyway, nothing that I've actually done. I'll look into that. But anyway, back on topic. So what we have to do is obviously quite a few different things with the eBGP. So first for eBGP is we need to have the right IP addresses configured on those interfaces themselves. Now for eBGP, the links are usually directly connected to one another, i.e. what that means is we've got these routers here and we've got these routers here, and you can see they're actually directly connected to one another. That's not always the case. You can have eBGP peering that's one or two hops away from each other, but usually these are directly connected interfaces from one router to another router, and then they just exchange their prefixes, what's called the network layer reachability information, i.e. what's out there in the internet via each other from one AS to another AS. Whereas on a iBGP we use the loopback addressing. So what that means is this router here is going to have a loopback address, this router here is going to have a loopback address, here's going to have a loopback address, here's going to have a loopback address, and so on and so forth. Now This is important. The loopback addresses are advertised via some type of interior gateway protocol, or IGP. So that would be OSPF, that would be ISIS. So I actually have ISIS running in this network here. I have OSPF running in this network here with different areas. I've got OSPF running here as well, and here and here. I've done all this in the background. I've not shown it on here because it's just going to make the display way too interesting, like the colors. But the IGP is advertising the loopback addresses throughout that same autonomous system. And we're going to come on to iBGP in a later video because it's a whole different rule set with iBGP compared to eBGP. But this is just to begin with what BGP is. It's two different families. It's got two different ways of configuring a BGP. You can do so between different autonomous systems. That would be eBGP. And if it's inside the same autonomous system, it would be using iBGP. And I said a word quite a few times there, autonomous system, or ASN, autonomous system number. Now there's quite a few different reserved numbers and private numbers and public numbers for the ASN range. But really, just from a basic point of view, all you need to know that an ASN, an autonomous system, is basically an autonomous system in itself. So all these routers here will be within the same autonomous system. And whoever's network that is, they are obviously responsible and have the configuration rights for that whole autonomous system. That's basically what an ASN actually is. Now with BGP, unlike other protocols which are OSPF, ISIS, RIP, eIGRP in the Cisco world, where they're really just layer 3, BGP is also a little bit more different. It uses TCP to actually establish that connectivity. Now, if you know TCP, you'll know that it's actually a few different messages back and forth between a client and a server to establish that TCP connectivity. So with TCP, you're going to have the SYN, then we've got the acknowledge, and then right at the end, we're going to have the SYN ACK, if I remember correctly. I'm really not liking what my pen's doing here. it's very interesting. But regardless, BGP needs TCP to establish connectivity between two different routers via those two different interfaces. Until TCP is established, BGP will not send any adjacency information from one router to another router. And TCP for BGP is using port 179. So this is the port that will be used between different routers to establish TCP connectivity. So that's another thing about BGP, is it's connection orientated. It must have a stateful connection between different routers. Where with OSPF and all these IGPs, honestly, I don't know what they use. They might be using UDP. I suspect so, but TCP is definitely needed for BGP connectivity for both eBGP and iBGP. But let's ask the question, what is iBGP in the first place? Well, iBGP basically makes the internet work, and this network, this is why I've designed this network, is quite realistic to a degree of what is configured up there in the cloud, where we've got our different enterprises. So that could be business A, business B. It really doesn't matter. It is a network that an enterprise owns, configures, etc. And obviously then they want to access other resources outside of their network, but they don't have that reach, do they? Now inside the autonomous system, inside that network, they're going to have an IGP running. We know already that we're going to have eBGP running in between different autonomous systems themselves, different networks, and then we're going to have, for peering and to learn what's connected out there in terms of the internet, we're going to have iBGP running, not throughout the entire network, the interior network itself, but certainly at points in the network itself. We're going to have iBGP there on top of iGP. Now, if we look at it from Enterprise A's perspective here, it's peering to two different service providers. We've got peering here to ISP1, and we've got peering here to ISP2. Now this is obviously very important for redundancy purposes. If this link here goes down or something happens completely to ISP1, the network is just gone. You've got a network typically wants some form of resiliency and what needs to be connected to the internet, to services, because over here you might have a server or something, some kind of application which users here want to actually access. Whether it belongs to the same enterprise or not is a different subject entirely, and really not important at this point. But we obviously always want to have the up connectivity because so much is connected up there in the cloud these days, isn't it? So what typically would happen, and what I'm going to do is I'm just going to actually remove ISP2 here completely. So say ISP2 doesn't exist right now. So right now Enterprise A only has connectivity to this service provider here. Now what the service provider would then do is they would advertise into Enterprise A some block of IP addressing. Now that might be a static or DHCP assigned address, but typically it's going to be static from my experience and knowledge. They're going to assign a block of an IP address, and just for example it could be, and I'm just really making this up, that could be 200.100.0.0/16, just for example. I'm just making that up. And what Enterprise A would then do is they would then distribute this block of IP addresses, yes, to their users, but obviously to their own servers, to their own data center farms, whatever it may be, for them to have their IP addressing. And then what they'll do is they'll basically use this BGP connectivity to advertise out of their network into the internet through all these different service providers that are connected together to say, yeah, this is my IP address and this is what's configured. There'll be some form of NAT, different topic, but this is what I've basically got in my network. Go advertise this out to the world so external users can actually connect to me in the first place. But let's say in realistic networks this happens. You have a network that is multi-homed or dual-homed, I think actually it is. So we've got a connection to two different service providers. Now, when ISP2 was out, we had ISP1 saying, well, here's your IP address block. The problem with that is that if Enterprise A moved to another service provider, they're going to get a different block of IP addressing. And so they then have to change the entire IP addressing which they want visible to the internet throughout the entire network. So it's not good. It's obviously doable, but it would require a lot of work. So in a dual homed environment where you're connected to two different service providers, you're now no longer going to be getting that IP address block. Typically what that enterprise would do is approach a local registry. I can't remember what it is for Europe, but I know it's called ARIN. I forget what it stands for, but it's basically a body which actually assigns out huge IP address blocks to different end users and networks. And the whole idea here is to build that global BGP routing table. I think around this time it's around about 800,000 routes exist on the global BGP routing table. So it is quite astonishing. I'll try and find that for a later video actually. But this enterprise here would approach the the continental registry body and say, I need to be connected to the internet. Can you please give me a block of IP addressing? And let's just say, the ARIN or whatever it is here for Europe, they would come back with, and it just happens to be the same, just to keep things simple, they would come back with their IP address block saying, oh yeah, you've got a /16 network, do what you want with it throughout your network. And then what that network would do would use BGP to advertise into those service provider networks saying, this is who I am, this is my address block, this is what I want to be connected to the internet, out you go. And then the service providers then would advertise that information throughout their network and all the way to other networks as well. And that is essentially why we have BGP, because if we did not have BGP, regardless of how well configured and architected and network security, etc., it is inside the networks themselves, networks wouldn't see each other. Different networks wouldn't have visibility of what's out there. So yes, we need service providers to connect the pieces of the puzzle and connect everything together. But the underlying protocol is BGP. BGP is what makes everything work at the end of the day. It's what makes the internet work. And also with BGP, it's what's known as a path vector routing protocol. And that's a big word there in terms for BGP path. There's lots of attributes known as the network layer reachability information. There's lots of attributes that BGP look at to determine what is the best or shortest path to get to the end destination. When we look at IGPs, really what they do is they just look at what's the best metric or what is the lowest metric to get to any given destination. BGP is quite different. We don't look at the metric. There is, multi-exit discriminator, which I think is very similar to the metric in a roundabout way. But really we're looking at path attributes. One of those, just for example, is the AS path. Here, BGP looks to see what is the shortest path to get to that destination, and it's also a loop prevention mechanism. We're not going to go into full detail into this, but say for example here we've got autonomous system number 65100 here. Now, as packets go from a source to a destination over here, and let's just say the packets come out here, what Enterprise A does, it says, this packet has come from autonomous system 65100, just for example, and it then goes through ISP1, and then ISP1 prepends its autonomous system number when it's sent out through eBGP into Enterprise B, saying it's come from 1 because we've got autonomous system number 1 here, and it's also come from 65100, which obviously is the source itself. And then it comes into Enterprise B, where it would, in this example, actually terminate at a certain point. But just say, for example, it somehow makes its way back through ISP2, in ISP3, sorry, then into ISP2, and then back into Enterprise A. What Enterprise A would see is it would see its own autonomous system number in that AS path, and it then knows, there's been a loop here, there's a loop in the network somehow, let's just discard that packet. And that's how BGP can actually break. It is a loop prevention mechanism, but that's one of the many ways that BGP can break. So these are the different BGP states, and right at the beginning we've got idle. For me, this is like the OSPF down state. It's very similar, meaning that the routers, they're just sitting there idly. They're not really doing anything right now. It's only when you enter in a BGP configuration do we then start to move away from the idle state. But it will not start sending the network layer reachability information really until we get all the way down here into that established state itself. So it's got a few steps to actually go through. However, recall I said that BGP uses TCP. So once you enter in the relevant configuration that we're going to go through in a few minutes on the routers themselves, what BGP will initially do is establish or try to establish that TCP connectivity. And as I said, we've got two different routers. So I'm just going to do R1 here, and over here we've got R2. And what they're going to do is they're going to send TCP messages back and forth to establish that TCP connection. And again, that's going to be SYN, ACK, SYN-ACK as well, and all using port, TCP port 179. When that TCP has been established, not established down here, but established successfully, then we're going to move from idle into the connect state. Now you can actually see I've missed a step here. The active state is when something's not going right with TCP itself. It might be the link is down, or maybe there's segments being dropped, packets being dropped. Maybe the segment size, I don't know how big the TCP segments are for BGP. Can't imagine they're very big. But if there's fragmentation occurring, some kind of loss, anything like that, we are then going to go from idle into the active state. What active means is that router or routers are actively trying to get TCP to actually work, to actually be connected before we go into the connect state. Now, by default, and as far as I'm aware, you can't actually change this, there's something known as the connect retry timer. And the default here is 120 seconds. So a router will stay in the connect retry state, i.e. active. It's going to actively try to get TCP back up and running, or up and running, for 120 seconds, 2 minutes. Now, if the TCP is then established between routers, it's going to move into that connect state here. If it fails, it's going to move back into that idle state here. If it's passing as such, it's going to remain for a certain period, i.e. 120 seconds, in the active state itself. So ideally we don't want to go into active, we want to go straight from idle into connect, i.e. we've got the TCP connectivity actually established, it is connected. That's what the connect state is. The next step, when we go from connected into open sent, is when we send one of those BGP messages. So I'm just going to write messages here. So open is one of the very few, actually, there's only about 5 or 6 without me counting, type of BGP messages. And open is like the OSPF hello packet. However, where in the OSPF hello packet, it was containing certain information. The open message is actually doing the same thing, but it's not containing as much information. But what it's allowing is those two different routers which have established that TCP connectivity to check, do these values actually match? And if they match, we are then going to proceed to the next stage. If they don't match, guess what? We are going to go back to one of these previous points. Now, what the open message contains are values such as the ASN, the autonomous system number. Now, depending on the type of BGP, i.e. if it's eBGP, they have to be different autonomous system numbers. However, if it's iBGP, interior, it has to be the same autonomous system number. It all depends on what you've configured on that neighbor command. Also, what has to be unique, i.e. it cannot be the same, is the router ID, the identifier. If you've got two different router identifiers, that's great. However, if it's the same router identifier, this point is going to fail, and we're actually going to go back from the open sent, and we're going to fail back to one of the previous states. What we've also got, just like anything, we've also got security as well. So I'm just going to put sec. So with BGP, there is a certain level of security. And if you've got one router configured with security on the interface and another router without any security or incorrect security settings, obviously the peering is going to fail. And again, we're going to drop back from the current state to one of the failed states. I probably go back to idle. Also, we've got the version itself. So say, for example, it's version 4. IPv4 on one router. We need the same version on the other router as well. And I'm just going to write it all the way at the bottom here, the hold down timer as well. The hold down timer does vary from vendor to vendor. So in the Cisco world, it's default 180 seconds, I believe. In the Juniper world, it's default 90 seconds. But regardless, the hold down timer is quite literally how long are we going to hold this connection down without hearing from the peer. So what we want to hear every 30 seconds in the Junos world is what's called, and it's another message, the keep alive. So the hold down timer is 3 times the keep alive message. So in Junos, the keep alives are sent out every 30 seconds, hence the hold down timer is 90 seconds. So I would assume in the Cisco world, keep alives are sent out every minute, and hence the default hold down time in the Cisco world is 180 seconds. However, what the keep alives are doing is it's like a heartbeat. It's like CCMs. It's keeping the adjacency up. So the hold down timer has to match as well between two different BGP speaking routers, whether it be iBGP or eBGP, doesn't matter. That value has to be identical. So we've got our open message, which is sent initially. So in the open sent, what you have is you have one router sending an open message. So we're going to send, R1's going to send an open message to R2, and at that point it would have transitioned into the open sent. When or if it receives, ideally when it receives back the open message from R2, it will then transition into open confirm, i.e. I've sent an open message, I've received an open message, and now we are going to move on to that final part of this BGP process. So what are we doing in this actual open confirm state? Well, what we're doing in this state is we are waiting for one or two of different messages. We are waiting for either a keep alive message, which has to be received within that hold down timer, or we're waiting for the other type of BGP message, that is the, and I'm running out of space because it's quite a colourful screen, it's called the notification. So within that hold down timer, we are waiting for one of two messages, either the keep alive saying, yeah, I'm still here, I'm still here, I'm still here, let's keep this adjacency, this peering up and running, or we're waiting for that notification message. If during that hold down timer, 90 seconds default again on Junos, if we do not receive one of these two messages, we're going to move from open confirm all the way back to idle. So it's obviously not ideal. But what is the notification message? The notification message is basically saying there's something wrong with this actual adjacency. There's something wrong with this connectivity. So in summary, what the notification is doing is saying there's an error of some sort. Now at this point, BGP is not really going to care what that error is. So if there's a notification message, i.e. there's an error, we go from open confirm back to, guess what, idle. And again, if we don't receive that keep alive within that hold down timer, yes, it resets, but it will again go back to idle. Now, if we get that keep alive message within that hold down timer, we then move from open confirm into the established state itself. We have established peering between two different routers. The fourth message is what's called the update message. Now this is where we have got to the established state successfully, and I've tidied up the screen as you can see. But in the update message, this is where really all that magic happens with BGP. So within the update message, what we're going to have is network layer reachability information. So this is really the prefixes that can be reached. These are the networks, and associated to every prefix, either network layer reachability information, what we are also going to have in that update message is path attributes. The path attributes is defining a lot. It's defining all the different attributes of BGP, such as AS path. Remember, tracing where packets have been, where they're going from, where they've gone through, seeing if there's a loop. But you've also got other attributes such as origin, next hop, multi-exit discriminator, router ID, IP address. In the Cisco world, you've got wait. In Junos, we don't have that. In my opinion, there's absolutely no need for it. But the path attribute is basically defined for all that network layer reachability information. What is the cost as such, not metric, but what is the best path, the shortest path, etc., to get to that given destination. But in the update message as well, you can also get withdrawn routes. So withdrawn are all routes which are now withdrawn as such from the network, from the internet itself. So the update message, as I said, is where really all the magic actually happens. And there's actually a fifth message that a lot of people do forget about. And you could argue this case, I'll be fair, but it's the reset message. So TCP doesn't really work well with reset. It doesn't work at all with reset. But there might be occasions where actually you want to reset the adjacency between different routers so that they can update the BGP table. Because as I said, TCP doesn't like that. So what we've got is we've got a hard reset where you quite literally tear down the adjacency itself. Or you could do a soft reset where you're doing a soft reset, you're keeping the adjacency up, but you just basically want to refresh all the information that you've got from that peer itself. And you guess what? You could do this in and you could do this out. In being I want to do a soft reset, a graceful reset on all network layer reachability information and path attributes that I've received from peers that have come into my autonomous system. Out being I want to do a soft reset on all attributes and networks, etc., that are going out of my autonomous system. So these are the different states and these are the different messages. So as you can see, it's quite a few different steps to go through. Ultimately what we want to get to is this established state. But at any point, if a notification message is received indicating some type of error, or that hold down timer expires, doesn't matter if we're in open confirm or in established, it's going to go all the way back to that idle state itself. So those are the different states, those are the different messages. What we're going to do now is actually go onto the lab and do a basic configuration on the Juniper Junos devices on how to build an eBGP peering between two different autonomous systems. So as I said at some point during this video, I'm not going to go through the configuration and the rule set of iBGP. It is quite a bit different to eBGP. So the focus now is on how to build, it is a basic configuration, but how to build an eBGP peering between two BGP speaking routers. So just anywhere on the network, what I'm going to do is actually build the peering between this router here and this router here. So we're going to build the peering from Enterprise A, which is an autonomous system number 65100, to the ISP 1, which is in the autonomous system number 1. So we're going to build the peering between here, and what we're actually going to do is we're going to use Wireshark to actually look at these BGP messages, those packets, as they're being sent and received on the wire itself. And I'm not just saying it, but the configuration on how to configure BGP to establish peering is incredibly straightforward on Junos. So I've got routers R5 here and R1. I'm just going to start off with R5 in ASN 65100. So the first thing we need to do on these Junos devices is configure the local autonomous system number. So for this enterprise, for Enterprise A, it's autonomous system 65100. Where do we actually configure that? It's in the routing option. So if I just do a quick show routing options, you can see I've already configured the router ID, but nothing else. So all I need to do is do set routing options autonomous system, and then I enter in 65100, and if I enter that same command again, we can now see it's there, but again, not committed. That's the local autonomous system number, and that is the master 65100. The reason why I'm saying this is because we can actually override that master ASN when we go into the BGP protocol. So let's do edit protocols BGP, and you can see, of course, there's absolutely nothing here configured. That's obviously going to change. Now, to configure an iBGP or an eBGP peering, either one, what we do need to define is an actual group. So here I'm just going to say set group, and now we need to give it a group name. Now I'm going to call this external, and because we're peering to ISP1 in autonomous system number 1, I'm going to call it S1. So I've done set group at external autonomous system 1. Now all on the same line, I can then enter in all the small amount of configuration really to enable this eBGP peering. But for now, I'm just going to hit question mark, and you can see there's a lot that we can do. As I said, BGP is a very big protocol. So we can override the autonomous system. We could do authentication. We could do BFD, BMP. I don't even know what that is right now, to be honest. We could do IPsec. We could change the whole time. We could go into family, INET, IPv6. You could see there's a lot, of course. But what we do need to define, because this is an eBGP, i.e. it's external, is we need to define the type. So if I enter in type and hit question mark, you can now see I can enter in to be internal, iBGP, or external, eBGP. We need this to be external because we are creating a peering from Enterprise A to ISP1, i.e. from Autonomous System 65100 to Autonomous System 1. So I'm going to give it type external. Now we need to define the peer autonomous system. Because this is external, we need to say who we actually peering to. The reason why we're doing it in this case is because we might be connecting to a switch which has multiple routers connected to it, all with different autonomous system numbers on their configuration. So we need to define who we want to peer to. So I'm going to enter in peer. And just like we do in the OSPF world when we have a point-to-point network, we need to then define the IP address of who we want to build that adjacency to. Now, this is where that neighbor command comes into it. Now, I can see the remote end of R1 has the IP address of 170.10.20.2/30. That's why I need to enter in here without the subnet mask. So 170.10.20.2. That is the GigE000 interface on router R1. Now, if I just hit enter here and do show, you can now see that the group is there. It's been configured, but not committed yet. Coming back to when I said that we have this master autonomous system number. So if I just do top show routing options, we can see that is our master autonomous system number right there, 65100. What you can do, however, if I do set group external and it does it for me, is I can define what is my local autonomous system. So I can now define it to be, just for example, 65099, just for example. And if I hit enter and do show again, you can now see we have taken that master autonomous system number and we've now replaced it with a local autonomous system number at the group level. And this is really a big thing in the Junos world when it comes to BGP, is we've got a master configuration, but then when we go into groups, it gets more specific. So you can override that master, and then we can also go into the neighbor level and define different attributes at the neighbor level, which are then more specific than the group. So in summary, a neighbor configuration overrides that of a group configuration, and group configuration overrides that of that master configuration. But what I'm going to do is I'm actually just going to delete, not the group. I don't want to do that. So I'm going to do delete group external local AS. Let's just do show, make sure it's gone. Hit commit and quit. And that has now committed successfully. Of course, that is just one end of the link itself. We also need to go into router R1 and do the exact same configuration, but now pointing towards ASN 65100, i.e. router R5 over here. And again, what I need to do is define the master autonomous system number. And I'm going to give it the correct autonomous system number of 1. But again, we can define a different autonomous system number at the group level or even at the neighbor level. Junos has that flexibility to it. But what I want to do here is just do set protocols BGP group. Now I need to give it a group name because I'm coming from autonomous system number 1 and peering to enterprise A. I'll just move the box out the way, and because I'm peering to 65100, I'm going to give this the name of external because this is eBGP, and I am peering to 65100. Now I will also define the peer autonomous system 65100, give the neighbor address, so that is the IP address configured on the remote end of that link. So this is 170.10.20.1, and I forgot to do type external. So there we go, type external. And now if I do show protocols, you can actually see, yeah, there's the ISIS configuration. So here's the configuration I've done for ISIS earlier. As I said, I'm not going to go through all that. I've got other videos. If you want to see those videos, here's a link. But now you can see the BGP group external. That group is external, it's eBGP. I'm peering to Autonomous System 65100, i.e. Enterprise A, and that has this neighbor IP address of 170.10.20.1/30. So let me just quit this, and now if I do a commit and quit here, that is now committed successfully, and I'm back into the monitor mode, and I want to run through just two show commands. So the very first one I want to do is do show BGP, not BPG, BGP, and I think it's summary. Yes, it is. So show BGP summary. This is great because it just gives you a high level summary of the actual. I'm just going to do that command again so it's fully laid out. So here we can actually see who we're peering to. So this is from R1 to R5. So this is R5 here. It's in Autonomous System 65100. I've 3 packets coming in. I've sent 2 packets out. There's no packets out which are queuing. So if you saw any there, you might want to look into is there any policies which are causing any delays. When was the link last down? So it was down last 22 seconds ago, which sounds about right. And what is the current state? So it's currently established. And because there's nothing really configured here, I haven't defined any policies to do any kind of exporting of these internal networks, which are learned from the ISIS routing protocol. We don't have any active, received, accepted, or damped prefixes yet. Obviously that will change in later videos, but for this purpose, for this example, that's successful. We've gone from that idle state straight into the established state. And I'm just quickly going to build the configuration, eBGP configuration between R10 here in 65100 and R15 in ASN2, because I did say I wanted to show you a few packets on Wireshark. So it's always good to practice this. So I'm just going to do configure, set routing options, autonomous system number, and this is 65100. I had to check that just then. And now I want to do set protocols BGP group external AS2. The peer autonomous system is 2 with the neighbor address of 170.10.20.6, and the type is, and it's not going to let me do it all in the same line, so I'll just delete this quickly and do type external. Let's do show protocols BGP, and that's there. So I'm just going to commit to this configuration, and that's committed. And now what I'm going to do is I'm actually just going to do a Wireshark on one of these interfaces just so we can see those BGP messages going back and forth. So I eventually got Wireshark running on one of my routers. So I've got it running on the GIGI00 interface, which is on R15 itself. You can actually just see it in the headline here, and you can actually see TCP segments in an IP packet going to and forth already between routers R10 and R15. However, it's not building the establishment because we haven't configured R15 yet to have that. But you can actually see here TCP port 179. We know that is BGP. But let's actually go into R15. I'm just going to move this over here so we can actually see those packets coming down at the same time. I need to keep this here because I need to remember the IP address of the remote end, the interface on router R10. But let's go into configure mode. Let's do set routing options, autonomous system 2. And now let's actually define the protocol itself. Let's do set protocols BGP group, because we always have to define that group, external AS 65100 type external peer autonomous system 65100, and we need to then define the neighbor. This is why I've not made the Wireshark display even bigger, because I need to see the IP address of 170.10.20.5, and let's do show protocols BGP. I just want to make sure it's there and I'm happy with it, and let's hit commit and quit. And as soon as I do this, I'll just maximize this display now. There we go, it's a bit better, but hit commit and quit. What we should see is all those BGP messages flowing back and forth. We're not going to really see update messages, but we will see some BGP messages going back and forth to establish that BGP connection. And there we go, right there. So we could see a keep alive message there. We could see that open message. That's brilliant. This is where just the theory comes into practice. I love this. the open message. So now we've got the BGP open message, and we can go into further detail here. I can see the version 4, that has to match between the different autonomous systems, either routers. We've got my autonomous system. We've got the hold down time. Again, on Junos, it's 90 seconds. We've got the BGP identifier. That is the router ID, optional parameters, and more. Oh, and we've actually got an update message. I wasn't expecting that. So now we've got an update message, and there's nothing really in there. It's withdrawal routes none, total path attribute 0. Yeah, there's nothing really here. This just looks like some kind of broadcast message. But those are the BGP messages going back and forth. Keep alive. Hopefully we don't see a notification message at any time, because that would be an error, of course. But that is how we configure the eBGP peering on Junos devices. And so there we go, everybody. That is the end of this video. I hope you found that informative. I hope you found that useful. Again, BGP is a massive protocol. There's so much more information to go through, and the purpose of this video is really just to touch on the basics, i.e. what is BGP, why is it here? As we know, it basically makes the internet work. Without it, forget it, we wouldn't have the internet. And what are the different flavors of BGP? We've got eBGP for connecting different autonomous systems together, and then we've got iBGP, which we haven't gone through in great detail, but iBGP is for internal to that same autonomous system. And we've also gone through the BGP messages, the open, the keep alive, the notification, the update, and also the reset itself, and those different states of BGP. So, hope you found that useful. If you like this video, please give it a like, please subscribe, please message me if you have any questions. Until the next video, thanks for watching and stay tuned.